Section 4.6 is related rates. This is another application of our derivatives. So let's look at some of this. Write down what you think you need. Strategy for solving related rate problems. 1. Understand the problem. In particular, identify the variable whose rate of change you seek and the variable or variables whose rate of changes you know. 2. Develop a mathematical model. Sometimes drawing pictures help, and because a lot of times this is a geometric problem. Label the parts that are important to the problem. Be sure to distinguish constant quantities from variables that change over time. Only constant quantities can be assigned numerical values at the start. 3. Write an equation relating the variable whose rate of change you seek with the variables whose rates of change you know. Again, often geometric. 4. Differentiate both sides of the equation implicitly with respect to time. Follow all the rules. Chain rule is particularly important because you'll be differentiating with respect to t, time. 5. Substitute values for any quantities that depend on time. Notice that it is only safe to do this after the differentiation step. Substituting too soon freezes the picture. In other words, we no longer are a rate of change problem, but a constant. 6. Interpret the solution. Make sure that you decide whether or not the results make sense. Alright, so let's do a problem together. Write down the critical information. A police cruiser approaching at right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.8 miles north of the intersection and the car is 0.6 miles to the east, the police determine with radar that the distance between them and the car is increasing at 15 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of the measurement, what is the speed of the car? So I want you to take a minute and break down, are there any known rates? Are there any unknown rates? Are there any constants we have to be careful of? And see what you get. Okay, I'm going to use a blank screen and break this down a little bit. I'm going to draw a picture. So I've got a police cruiser traveling from the north. I have a car moving to the east. I know that, let me back up and do it in the order they gave it to us. So from the north, okay, so when the cruiser is 0.8 miles north and the car is 0.6 to the east. So the cruiser is 0.8 north and the car is 0.6 east. At this instance, I keep going the wrong way, sorry. The police determined that the distance between them is increasing at 15 miles an hour and the cruiser is moving at 60 miles per hour. So, the police are moving 60 miles per hour south. The distance between the two cars is increasing at 15 miles per hour. And I want to know the speed of the car. So label some of the rates that you know and some of the rates that you don't know. Alright, since this looks like an XY axis, I'm going to call this Y, this X, and I'm going to call this Z. So I know first of all that the police who are traveling south, dy dt, since they're going south and Y is decreasing, that's going to be negative 60. So there's the first rate that I know. dz dt, the distance between the two, sorry, I don't know why my pen does that, is 15, and it is positive. And then I'm looking for dx dt, and I'm looking for that at the moment when x is 0.6 and y is 0.8. So I know these two. I am looking for this at this instant in time. So now, using my numerator variables, my x, y, and z, because those are the rates I'm looking for, I'm going to write an equation. Well, this is a Pythagorean. So differentiating this, 2x dx dt plus 2y dy dt equals 2z dz dt. Now I'm going to plug in everything I know. X is 0.6, dx dt I don't know. Y is 0.8, dy dt is negative 60. Z, well, I wasn't given it, but this is a Pythagorean triangle, so z should be 1, and dz dt is 15. So taking a moment, multiplying these out, doing some subtraction and some division, I will ultimately get dx dt equals, I didn't do the math. Well, let's pause for a moment and do this. Okay, and I think on the next page we've got it. Okay, so here we go. They're going to do it for us again. So distance, the police car, distance between the two cars. And again, I think drawing that picture really helps for this. But doing it the same way we did, there it is. There's where we are. And then they get 105 for our dx dt. So the car is traveling at 105 miles per hour. So again, this is something that we've done before, I hope. So keep in mind the process, listing your known rates, your unknown rates, and when, what instant in time do we want to calculate this, differentiating and plugging in our values. So that's the only example we're going to go over. We'll do some more of this in class. The next several screens, which I will scroll through fairly quickly, but when it comes time, if you want some additional problems for the chapter test that will be coming up after our break, these screens give you some problems to take through the chapter with all the worked out solutions. So I'll just scroll through these. You can quit the video now at this point if you would like.